Very good afternoon, all, and welcome back. Today, we are going to probably wind up the semester's lecture classes. And I'm sure in the last classes, what we discussed was the job sequencing and the DP solution for the corresponding problem. And I'm sure you have practiced that and done that 01 knapsack DP. Today, we are continuing with another interesting problem, which we couldn't do earlier over the graphs. And in the graphs discussions, we have already discussed the single source shortest path. And effectively, we have discussed a lot of algorithms. Most of them were greedy in nature, like De Castro algorithm, etc., where we could make a local optimal choice and then we work over that. But now, at that time, I told that all pair shortest path is another domain of the problems. And those are also having some good algorithms existing, and we need to solve them also. But we couldn't discuss those problems or those solutions at that time because effectively it is dynamic programming based solutions. So at that time, we had not studied the DP, so we couldn't do that time. And today is the right time to, in fact, talk about those algorithms or start the basis of that. So today we are going to talk about this using a DP, all pair shortest path. Of course, finding all pair shortest path, one alternate can be that we can directly use single source shortest path. And for single source, you loop over this because in this case, the source is fixed. So loop for changing the source. And your source can be, or start or source can be changed from 1 to n. And then accordingly, you can have the corresponding all pair shortest path found because single source shortest path will find from source vertex to all other vertices, the shortest paths will be found. And instead of that, if you repeat your start to go to every vertex, so we will be able to find all pair shortest paths. All pair effectively mean from every vertex, we should be having knowing the shortest path to all other vertices. So this will require the shortest path computation from every vertex to every other vertex. And of course, same vertex to itself, that path will be obviously, the distance will be 0, etc. So that is what we want to find out. So of course, alternate one could be the looping of that. So whether I use De Castro algorithm or I use DAG or I use Bellman-Ford, all those have been a single source shortest path. And of course, I can loop over them. And then using loop, I can find all pair shortest paths. Fine. That is also not a bad method. That's also a good way to do. But today we will see a more interesting because the dynamic programming has its own advantages and looping probably sometimes could be doing some unnecessary computations also. So today we will see a DP based solution that is alternate 2 and DP based all pair shortest path will be done. Of course, for this computation, the algorithm which we are going to talk today has an assumption that negative weight edges are allowed, but negative cycles don't exist. So assuming this concept, we can straight away go and discuss the problem. I need not repeat what is all pair shortest path and what is single pair shortest path, etc., etc. All that is well known to you. So I say how to solve. Solving it DP based effectively requires that you have to follow the steps. So of course, first step being characterize your problem, and characterization in fact effectively requires your optimal substructure and sub-problems. So you have to find optimal structure and effectively sub-problems, which probably or most likely they will be overlapping in nature. So effectively, you have to primarily define this. And once you are able to do that, then you can find out a recursive definition of course that will use your substructure or sub-problems. and sub-problems or sub-solutions, they will also be optimal in nature, and they will be combining together to solve the bigger problem. And directly from there, my coding, etc., will be possible. So, first step is quite useful, characterization. Let me just shift this other side so that now you can easily see other way. So, characterization. Characterization of any problem for making its optimal structure using recursion, using sub-problems. Obviously, if you remember, in every problem like rod cut, MCM, LCS, I said intuitively assume you know the solution, and then we try to find out some intermediate K. K for intermediate solution known, and based on that, we made our subsequent solutions. And we assume this is known as a guaranteed measure to us. So I want to solve. I want to find out a path from some vertex I to J. So in general, I say shortest path from I to J is to be found. Effectively, that is notated as I, and I say there is a tilted line drawn to show there is a path. When I say I to J, it's a directed edge. And when I show IJ, it means undirected edge. And when I show a tilted line like this, it shows a path. And path means what? Path obviously means one or more edges in sequence in a particular order. How many maximum edges? If I have a graph, what are the most maximum edges of this? Assuming there are no negative cycles, I'm sure you know how many maximum edges can be there in a path. Yes, you are right, probably. If there are n vertices, obviously the maximum edges will be n minus 1, because each vertex will get covered, and for going through all vertices, the path remains the shortest. So maximum can be this. So in general, I say a path of m edges, where m will be in the range of 1 to n minus 1. Of course, if m is a 0, that will mean no path exists or infinite distance will exist. So, but for a valid path, the number of edges included will be 1 to n minus 1. So, effectively, I show this as notation of SPMIJ. It means I want to find out a path of I to J traversal using m edges. Now, this problem I have to characterize for sub-problems. So, I always said we will be always trying to divide the problem into sub-problems, and for that they will be further used recursively. And for making that characterization, think of what I should take as a K, which is known to us initially and known intuitively. Later, of course, we will generalize and say this intuition, if not works, then how to work this. So I say intuitively known to us. That will obviously mean the problem should reduce to smaller problem, which will be solved further. So in this case, obviously, I'm saying path of m edges sub-problem effectively will mean something less than m. That will mean, let's say, m minus 1 or fewer edges. So if I think that I have to divide my problem into sub-problem, my logic has to reduce the size to m minus 1 or lower. So I say, let's probably now I can define my intermediate step, that I have K vertex known through which the path guaranteedly goes, or through which we reach to J. I say I know guaranteedly some K. For example, I say if I want to find path from 1 to 5, assume that I guaranteedly come to know that we will reach some way 2, 5 via vertex 7, 5. So let's say n equal to 8. I have total 8 vertices, 1 to 8. So I say my path, shortest path from 1 to 5 guaranteedly goes from 1 to 7 somehow, and then followed by edge 7, 5. This intuitively I came to know. So if I say that, this will become my k, and I am going to solve my problem using its logic. So what I said was, if I am trying to find shortest path from I to j for m edges, I say effectively this is nothing but I claim that this will be equivalent to SP of m minus 1 edges from I to some k, followed by the edge use of kj. And edge used of kj means the weight of edge kj. If I know this k, my answer is guaranteedly correct. So I'll just take this other side now. Yeah, so I say, I'll just repeat, I said SP of Mij is to be computed, where I said that sub-problem with m minus 1 edges will be solved for going from I to some k, which is k is known to me, and from there, weight of a kg. So collectively, this should be optimal if I want this to be optimal. My answer to be optimal if my overall this is optimal. Of course, that will mean this can be a recursive call. I can have this recursively solved. And overall this to be optimal means k should be best known to me. K has to be best. We assumed this is known, but actually it will never be. So how to find? The obviously try all possible values, and out of them choose the best. So that is a thumb rule to solve such problems. So I say effectively nothing but now I can claim that SP of Mij will be nothing but I will say try all k and find the minimum out of that. So minimum out of for all k I will try 1 less than equal to k less than equal to n. K can be all of these values, and I would like to find out minimum out of ik and weight kj. So that can be one solution, but this is always a recursive or sub-problem based. There has to be a non-recursive step. That also we have to think. Secondly, in the above one, we assumed that there is always going to be path of m edges. It is possible to think that the path could be of not full m size, path to be of m minus 1 edges or 1 edge also. Direct edge. That will mean 1 edge, m to be 1. In above case, we assumed some k exists. It is possible that no k exists and I have directly weight to be used. Yes, that will also be answered. So if I say like that, that actually means that I should find minimum not out of all k, but also out of something more. That a path directly existing for m minus 1 edges in between I to j. M minus 1 will recurse down to m minus 2, m minus 3, and finally m equal to 1 will also mean a direct edge covered. So it's not compulsory, but probably some of you could think that I should also imagine to think of having m minus 1 path without via some k, no k existing at all. Of course, this can be one possibility. And then for all k correspondingly trying and then solving it correspondingly in the same way. I claim this, that yes, this completes everything possibility, but probably this factor, even if comes to your mind, I will say it is not necessary, not compulsory. Why? Yes, some of you could say that like in road cut also, we could have the without cut also an answer. So that also should be covered. Similarly, in this case, if there is no intermediate edge direct also covered, that also should be taken. Yes, that should be taken, but I say writing this is not explicitly needed. The reason being, in this above, if I consider k equal to j, because when I'm saying for all k, it also includes a k. So k equal to j. K equal to j will mean it is equivalent to writing SPM minus 1 ij plus weight of jj. Weight of j means the edge from itself. So we always treat this as always as a 0. And in my adjacency matrix or anywhere else, you can normally store this as a 0 at the diagonal level. And accordingly, this is 0. So this becomes equivalently equal to SP of m minus 1 ij, because other part is 0. And if so, this value is exactly same as this one. Hence, I can say I have nothing special to be done, that if recursively it was solvable, it is equal to nothing but minimum out of for all k to be done, and k should be taken for all possible values, including k being equal to j. This becomes nothing but recursively solvable or mathematically solvable for ik and plus weight of kj. This weight will be needed for every calculation. Hence, I can easily see adjacency matrix representation will directly store these weights in the adjacency matrix. So this representation will be more useful or better easy to program compared to adjacency list based representation. So for all pair shortest path, adjacency list representation could not be as simple or as useful as could be the adjacency matrix. So maybe you can, sorry, I forgot to change this side. I'll just put here and then again explain. Yeah, so I said SPM of ij is equal to nothing but minimum for all k to be taken. And explicitly SPM minus 1 ij need not be written. That is already covered into this calculation. And I said weight kj is effectively directly needed for lots of calculations. Hence, adjacency matrix representation will be much more useful than adjacency list representation. So I can say now this is a directly mathematically defined recursively. Non-recursive step, that also should be known so that we can formally write the recursive coding for this. So non-recursive math oblique step, what should be there? Now you have to think of. So there can be multiple ways. Of course, you have to think what can be the point where non-recursively value can be calculated. Yeah, non-recursive means my path answer or path value is guaranteedly known without recursion. When is that known? Can you think of that? I'm sure some of you are able to imagine what can be there. For example, if I say path of one edge, it directly means from, let's say, vertex 1 to vertex 5. If the path vertex, if the edge exists, the weight is, let's say, 2. So the weight 2 will be answer. If no edge, obviously means path has highest value, say plus infinity, or path doesn't exist. So I can easily see for one edge, no calculations, no recursion needed, no optimization needed. It is a straight. That will mean I can say if m equal to 1, my value of SP, so I can now say in that case, the value of SP ij, SPM ij will be directly equal to corresponding weight of ij. If edge exists. If it doesn't exist, then I will take it as a big integer value. I'm intentionally writing big integer, not max integer, because if you write max integer, later in max int, if you add some value in the subsequent sets, some weight will get added. This will be overflow, value will become negative, and negative value will make it actually minimum. So that will be a problem. So instead of that, maybe take a big integer, but something smaller than max int. For example, if my number is a 32-bit, so I will take it less, let's say 30,000 instead of 32,767, which is max int in 16-bit. 64, 32-bit accordingly, that will be there. So 3767 is max int, but I will not take that, so that my overflow and that negative value, overflow will otherwise lead to a negative value after addition, which will be probably failing my code. So I will not do that, and hence I will prefer to do some big. But I say if m equal to 1, my weight is simply directly the value that can be non-recursive step. Of course, other non-recursive way can be that take it down to 0, m equal to 0 means no edges. No edges obviously mean weight, where the SP value will be either 0 or infinity. 0 if I equal to j, otherwise infinity because path doesn't exist. Because if I say I have to go from same vertex to itself, no edge is needed. So I can say my distance path will be also 0. Shortest path is also 0, and path is possible. For others, if m equal to 0 means without any edge, so obviously for I not equal to j, path is impossible. But obviously not much useful. So m equal to 1 will be a better choice to take it as a non-recursive, because through this lesser recursion will be needed and easier also, and easy to understand also. I can easily say m equal to 1 means one edge path. One edge path means effectively if edge exists, path exists, otherwise it doesn't exist. So I can easily implement and use that also. Having said that, effectively characterization is done. Then I have to write recursive definition. So let me just shift this side. So I'll say if I have to do the recursive definition, let me write correctly. So my recursive definition and all problem is just 5 minutes away from the total solution. Earlier I have written recursive, so I will say let it be a function call. So I'll say all pair recursive function to be written. What are the parameters I will decide? So what are the parameters? I have already written SPMIJ, means I need M because M will change later to M minus 1. I is the starting point, J is the ending vertex. I to K also needed recursively, so I can pass all these parameters. Equal to, I can easily see this was nothing but SPM minus 1 IJ. So I will say if non-recursive equal, this value is effectively equal to weight of IJ if M equal to 1. And otherwise, this is going to be equal to this value. This internally means nothing but all pair recursive with M minus 1. That means parameter will be M minus 1, I, and this was K taken, IK, plus weight of kj, and this was to be done over loop for k. That's it. So more or less my code is ready. I have nothing else to be done. The code is simply in this form, writable as a recursive function. So I can easily do that programming. So if I have to write a function, maybe I will say int all pair recursive mij being passed, and correspondingly, if m equal to 1, maybe I can say return correspondingly whatever I want to return weight of kj oblique big int. So whether big int is stored in my weight matrix or not, accordingly I can return. Else, or even if I don't write else, effectively I have to loop k times, loop k equal to 1 to n. And I have to every time calculate minimum out of, so I will say return minimum out of corresponding all pair recursive with corresponding k called m minus 1 I k plus weight of kj. And of course, weight of kj will be, if edge doesn't exist, it should be big int if edge doesn't exist. Now, using this concept, my code is directly ready and I can directly return this. Once I am able to return this, my work is effectively calculating weight of or shortest path of, let's say, 1, 5. So 1, 5 will be effectively possible to be called by using maximum value for m. What can be the maximum value of m? So that is obviously n minus 1. So if I try to calculate this, my weight shortest path of 1 to 5 will be computed. I want all pairs. If I want all pairs, so I need loops for ij. Ij repetition needed. But because in this code, I and j are not reducing in the recursive call, so hence I have to write a separate function the way in DFS, etc. we wrote. So I will say, fine, I can write a separate function where I can write all pair paths to be started. Whatever parameter I need, I can decide. But what I need here, I need for every ij, I need to call this recursive function. For I equal to 1 to n, for j equal to 1 to n. And what I need to call? I need to call the recursive function all pair recursive. What should be the value of m and I and j? So all values to be taken. Let's say I store it in some variable val, and then I can print whatever results I need, val and whatever, etc. So that will be giving a path between every pair. Instead of m, what should be passed? Obviously, what should be the maximum value? Because in recursion, we always start from the highest value and go top down. So maximum value of m is possible to be n minus 1. So I will send n minus 1, which will recursively go downwards towards n minus 2, n minus 3, and so and up to n, up to 1. So that way I can easily write that. Then going further, step 3, I have to effectively go towards DP storage and DP solution and bottom-up solution. So how to get a DP storage? What array? 2D array, 3D array, 1D array, what? So obviously now how to find that is directly dependent on my call being made. In this call, if you see, m is also needed and m is changing. I and j are obviously going to change. So for every ij needed, and for calculating path of maximum n minus 1 edges, it internally requires path of lesser m size also. Hence, m is also going to be needed. So effectively, I will need some value like mij will be the corresponding answer for shortest path between I and j. Now, that obviously means I need a 3D array. So I need 3D array int dp. Maybe let's say you will define 20, 20 or 30, 30, 30. But actually needed is I need 1 to m. That means my size should be declared as m plus 1 in minimum. This I require to go 1 to n. So I require this size to be n plus 1. In minimum, this is required 1 to n. I require n plus 1. Because element 0 index, I will not be using. So if I write m plus 1, that means 0 to m indexes will be possible. And those indices will be sufficient to use 1 to m. Hence, I need a 3D array like this to solve my problem. And I'm defining fixed size so that if you are making it as a parameter passing, it will be useful to you. Once you know this, the only question remains how to calculate. So how to generate DP array? How to generate that? Things are simple. Generation of a DP array effectively requires, again, nothing great or nothing special to be bothered, that I have to generate every entry of this array. Obviously, what way, what order of generation? So I'm clear that I need loop for m also. I will need loop for I also. I'll need loop for j also. All three loops needed for every path from I to j found. And that loop will be needed internally. My recursive call was using a k loop, so that will also come into picture. Already that was existing. So that will also come, but instead of recursive call, the DP will require these three loops. Which order they should be written in my coding? Now that answer will come, that what is my non-recursive value which gets defined? Because that gets value without any something further to be calculated. So non-recursive values, we could easily see we have done for m equal to 1. That will mean for every m equal to 1, all values of ij pair are defined without any problem, not to be calculated. Hence, these values can be directly used. So that straight away tells that m loop will be outer loop. And for every m, obviously 1 to n minus 1, my internally I loop followed by j loop will calculate dp1 ij first. Once all ij will be computed, then this 1 will change to 2, then this 2 to 3, and it will go up to n minus 1. So this much is sufficient to explain. And now you can easily do the analysis component also. The time complexity, you can easily see how much can be there. If I'm using adjacency matrix computation used, weight matrix is directly applicable. But I can easily see loop for m, within that loop for I, within that loop for j, and there I said for all k. So that effectively means or theta of n4. Of course, better algorithms or better solutions possible. So once you study in more detail, this theta of n4, same algo, can be improved to make a better solution with a small trick applied, as it will become theta of n cube log n. And then there are other DP solutions which are even better, like I exist or say Floyd-Walsh algorithm, Floyd-Warshall algorithm. which is again a DP based, but it will be even better than the current solution. So, and some more are there. So you will study in advanced data structure course. Advanced DSA will be another subject which you will study, and there you will study in more detail. So with this, I will stop my discussions, and probably my all programming or algorithmic related subject coverage contents are covered. This might be the last video for this subject. And after this, I'm going to show you the code for corresponding all pair shortest path for those students who are weak of this problem. So those who can do programming, they should try to do of their own. And those who want to see the solution immediately, they can see the next few minutes video. Otherwise, you can pause, try yourself. If you are not able to make, maybe you can come back anytime and do this part here. So I'll just come to this screen sharing. This is already shared. So now I can say, if I am having the corresponding all pair shortest path, so I'll say, first of all, recursive code. If m equal to 1, I'm supposed to return the corresponding adjacency matrix. If I assume this is a global variable, this value will be supposed to be infinity for non-existing edges. Other alternate could have been if using I equal to j and other alternate also. Otherwise, I have a result to be taken as a big int for k equal to 1 to n for k's loop, finding the recursive call with m minus 1 ik, and then correspondingly, I'll say val plus corresponding weight of kj compared, and then finding the corresponding minimum value. And whichever is the minimum, then I will be returning that. Of course, that needed for all pairs to be done. So I have a recursive start function, which is going to call all ij pairs. So I have two loops, and my recursive call for all ij pairs with m taken as n minus 1 called. And then finally, I will print which path I have already found. Correspondingly, I can have the enter number of vertices, this, and if needed, I can accordingly have the corresponding adjacency matrix read. So instead of initializing, I can have this all reading done. And then once reading done, I will say while reading, if you have given ij as 0, and because it was a non-existing edge, so I can initialize it to big int. Big int, as I said, I have taken intentionally as 32,000. Don't use int max because adding some value this to make it negative. For the time being, I have taken this array as a sample graph, but of course you can read and do that accordingly. Then comes the DP solution to this. So for DP solution, I have taken this array, distance or DP solution, and max I have defined already. So this array is declared. And now based on that, my DP solution is straight away effectively nothing but the same code. Whatever these two loops followed by this calculation, the only thing being this call will be replaced with a DP variable or a storage variable. So effectively, I start with this saying big int, etc. So if m equal to 1, that distance 1 is being computed. So this value m equal to 1 dp1 array for every ij being generated, the corresponding value or big int, and then from m2 to n minus 1 to be precise, this should be n minus 1, and 2 to n minus 1 I will implement, and then for every ij, the value will be computed. This value will be the corresponding distance based. I will put it into the same code as it is. The only thing is earlier it was a recursive call. Now instead of recursive call, it is a array based data. And then finally into the corresponding place, this result will get stored. And that's it. So later I can accordingly print the result. So in my main, initially I called all pair recursive start and all values printed there. Then I said via DP, I will call all pairs path DP, and then my 3D array is ready. Out of that, I will display the final result, which is at n minus 1 ij. I think this code is sufficient enough to describe, and I'll stop here. And then I'll ask you now to implement of your own. And of course, this code will help you in